Hello everyone, this is my final project demo, and my final project is to make a system that can control the tension of two cables by controlling the torque of DC motors. So let's take a look at the basic hardware setup. So obviously I have two DC motors. This is motor 1 and this is motor 2, and each motor has a cable reel connected to a weight scale in the middle, and this weight scale is sitting on a slider so that I can move this load cell back and forth. And the motor is sitting on a motor rack that has a load cell embedded in it. So this block of metal is a load cell that can measure the force acting on this direction, So the load cell is connected to an external analog to digital converter. So this little chip will pick up the analog signal from load cell and convert it into digital signal and send it through I2C and through this cable all the way to this servo control board right here. So this purple board, so I designed this purple board earlier, and this is essentially a shield for a STM32 nuclear dev board. So this servo control board will take in the load cell signal and then do a bunch of filtering and PID calculation, and then get an output signal that's essentially how much the torque command for a DC motor. So this torque command is essentially, this torque command will be converted into a voltage signal through this digital to analog converter, and this voltage signal will be fed to the motor driver on the back side of this green board. So motor driver, like this scene, so based on how much voltage I give to this driver will control how much current that can flow from this power supply all the way through this thick cable to this board and then to the DC motor. So I'm essentially control how much current, directly control how much current that can flow through this DC motor. Yeah, and then we can talk about the requirement for the system. So the system should be able to maintain cable tension not only under static condition but also under passive motion. So what does that mean? So if this cable has provide a 2 Newton of tension, and I pull this cable back and forth, the tension on this cable shouldn't change or shouldn't fluctuate too much. So why do I need this requirement? Because if I only provide a constant torque, a constant current to this DC motor, and I pull this cable back and forth, you will see the tension change a lot due to the internal friction of the motor. So if I push the cable to this direction, the cable tension would reduce, and if I pull this cable in this direction, the cable tension will increase significantly. So I don't want that, and so my entire system is basically trying to compensate these this internal friction of the motor. And aside from that, this entire system needs to receive the force command from my laptop. So my laptop will send a force command to the motor control board, not just force command, but also the stop and start command for the motor control loop. And these commands are sent to the motor control board through USB protocol. Okay, so moving on to the function demo. Let's start from resetting the servo control board, motor control board. So after resetting the control board, the control system will enter the stop state, which means the feedback control is not engaging, so the motor is doing nothing, and there's no tension on the cable. And let's go ahead and start the keyboard controller. So this is the interface that I designed. You can see here I show what kind of option you can have, what kind of control option you have. You can individually increase or decrease the force on each motor, and you can put the system into stop or start state. So when I first start the keyboard controller, the system state will be e-stop. Yeah, this section will be displaying the system state. So let's go ahead and start the system. So before I start, the cable has a lot of slackness in it. So once I start it, you can see the feedback control system kicks in, and it provides tension very quickly. So let's take a look at the system state again. The system state becomes running, and this is my initial force command, 2 Newton for both motor. And here is the actual load cell reading. So in real time. So if I tap the load cell slightly, you can see the reading changing accordingly. So let's see how well the system maintained the tension under passive motion. So right now, each cable provide 2 newtons of tension at this particular point, which means the net force at this point is 0. So let's take a look at it. Yeah, right now the weight scale is not subjecting to any net force. And if I try to move the weight scale, slide it around, you can see even though the force reading is fluctuating a little bit, but the amount is very little, very minor. So it's about like between 1 to 10 grams. So it's pretty good, at least much better than not having this type of compensation. Yeah. Okay, so let's try something else. Let's slide the weight scale to the far right, and let's try to increase the force on motor 1. Let's crank it up all the way to 4 Newton. Yeah, so as I increase the force command, you can see the force reading also increase, which means the feedback control system is doing its job. And because right now this cable provides 4 newtons of tension, this provides 2 newtons. The net force should be 2 newtons in this direction. Let's take a look at the weight scale. Yep, this is about it. So as I move around the weight scale, you can see the force reading is always very close to 2 newton, and that means my system can maintain the cable tension pretty well, even under passive motion. Okay, so now if I hit H key, and reset the force command, you see the force reading drop back down to 2 newton, and the net force on the weight scale becomes close to 0. Yeah, so as expected. And I can also stop the system by pressing 5. Once I stop the system state change immediately, and if I hit 9, I will exit the keyboard controller. And once I do that, the feedback control loop will be blocked, and the system will enter stop state. So the motor is no longer doing its job, and the cable becomes slack again. Okay, so that's my demo. I hope you enjoy it. Thank you.